Hi, welcome back. In this lecture, I would like to discuss measuring performance. While measuring performance sounds like an easy task, it does have its own challenges. So let's look at the example of these slides. We want to measure the performance of a very simple kernel that is the following. So we have a loop going from 1 to n, and then at each iteration we calculate the multiplication element by element of two arrays A and B and store the results in C. How do we do the performance measurement? Well, we take the time at T1 before the kernel execution and at T2 after the execution of our kernel. We calculated the total execution time as T1 minus T2 minus T1. So what can go wrong with this kind of performance measurement? Different things can go wrong. Let's look at the first one. So the first problem is the so-called problem of clock granularity or clock tick. So this might happen if our n, that is the size of two arrays, is very small. So what can happen is that the T1 and T2 time measurement can be the same, right? So if T1 and T2 are the same, the total execution time will be 0. So why is that? Well, the problem is that all the timers are not infinitely accurate. All the clocks have actually a granularity that is the minimum time that they can measure. The error in a time measurement, even if everything goes perfectly, might be the size of this granularity that is also called the clock tick. It's very important that we always know what is the clock granularity of our timers. And it's very important that also we, 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 we make a measurement that are much larger than the clock time, the clock tick. So our measurement are not affected by the granularity of the timer. As one of the assignment, we will actually calculate the clock tick of your timer on your system. For doing that, we're going to use the code that we provide in Canvas. So what this clock granularity.c does, well, is basically doing the very simple thing here in this measure here image on the left. So we have a loop going from 0 to n, where n is the number of time measurement that is provided through the command line. At each iteration, we basically record the time. So if, and then we plot here, on this plot here, the difference between the different ticks, right? So if the ticks have as the same value, the value will be 0. But if the ticks are different, then we'll have a finite value here, and it's plotted here. So we can plot it, and also we can calculate what is the minimum difference between different ticks. So in this particular case, I ran the code on my laptop. I did 500 measurement, and the granularity of my timer on this laptop is roughly 10 to the minus 6, right? So one question we have for your assignment is actually, can we do better? Can we have a better timer? So we are going to ask you to use a different timer using the RDTSC register on Intel CPU. So we are going to use this for your assignment, and hopefully we can do better than this 10 to the minus 6 granularity. A second problem that can happen is the so-called cold start problem. So let's look at it. So what happens when the code is executed? Well, the assumption we always have is that the code is ready to execute it. But code might still be on the disk and not even read in the memory. So there's some time to bring the code from the disk to the memory. Another problem we might have is that data might be in the slow memory rather than in the fast. So it might be in the main memory instead of the caches, which might be wrong or right for what we are measuring. If we want to measure, for instance, the performance of the caches, we want our data to be on the caches, not on the RAM. Vice versa, if we want to measure the performance of our main memory, we want the data on the main memory and not in the caches. In general, all the in all the cases, the first run might be longer than the typical measurement of the kernel we are measuring. So to solve this problem, we need multiple tests are often necessary to ensure that the cold start effects are not present. So in particular, there is some special effort that is required to ensure the data is in the intended part of the memory hierarchy. As I told you, if you are measuring, for instance, the performance of the cache, we need to ensure with some trick that the data is on the caches in order to measure the performance of the caches. A third problem we might have is that the compiler might be actually too smart. So why is that, right? So look at the example here. We have our kernel. We're measuring, and we calculate the multiplication of A and B, and we store in C. But the compiler might realize that actually C is never used after the measurement. So what it can do is actually eliminate this part of the code. So if the results of the computation is not used, like in this very simple example, the compiler might eliminate the code. So the performance will look impossibly high, like basically there's no code, so there's no operation here, so the performance will be very, very good. So in some cases, it also might give some performance results that might look plausible, still eliminating part of the code. So this is even trickier to catch it, right? So what we need to do is ensure that results are used. So one easy things is actually to add some code here, just using the values of C to ensure that the C variable is actually used. One other things that we can do is actually to check the assembly code and see the operation are there. As part of the assignment, we will also ask you to check very quickly what is the assembly code and see if the actual operation are there in the assembly code. A fourth major problem is the so-called interference problem. And this is due to the fact that other activities are sharing our processor while we are doing measurement. So might be the operating system, system daemons, and other users all interfering while actually we are doing the measurement. Also, some parts of the hardware do not always perform with exactly the same performance. So the performance results in general are not deterministic. So running the same measurement multiple times, you will never get, it's very likely you will get always the same performance results. And this is due to the fact that performance results are not deterministic. So it's very important when we do a measurement that we make multiple tests and we report different figures. So what do we need to report? So easy choices include the average of our performance measurement. We can include the minimum value because the interference slows the system. So is the minimum valuable must be probably the most reproducible value to get. So note that if multiple iterations are used to avoid clock tick problems, the best you can do is the minimum of an average. Also, what we can do is to, when we have multiple measurement, is to report the so-called box plot. So here is an example where we show all the data given the mean, the median, the first and the third quartile. So, one question we might have is actually how many measurements we need to do in order to have statistically relevant representation of our measurement. Well, this is a difficult question. There is somehow an agreement that if you have distribution of your measurement, you can actually plot it. a statistical relevant an, a statistical relevant number of different measurement is relevant when the distribution function approximate a Gaussian. Right? So how to report performance measurement in our papers, in our reports? Let's look at on something. So what is wrong with this reporting this time here, right? So if you report, you just put this number here. Well, there are two major problems. First one, we need to understand, what is the units. Is second, microsecond, millisecond, and second, so always remember to put the unit. And second, also, this measurement is affected by an error. So the major question is how accurate is your measurement. So you need to report what is the error of this measurement. In many cases, what we do, we take our different measurement, we take the average, and then we calculate the standard deviation, and then report the error as plus minus the standard deviation. You can also report the minimum value, the maximum value. You can report the error, the clock granularity as the error, right? So always give an idea about the performance variability of your measurement, reporting some error related to the different measurement that we have performed on the system. So if you want to start, continue studying HPC and you want to do research on HPC, it's very important that you look at this very important paper, Scientific Benchmarking of Parallel Computing System by Thorsten Hoffler and Roberto Belli. It discusses different errors that we are doing when reporting performance results. So in particular, is looking at when using arithmetic mean instead of harmonic mean and vice versa, is discussing the problem of statistical relevance, that is how many measurements we need to take, and many other problems. So this is very nice reading, and we all encourage you to go through this paper. So part of the assignment will be actually to solve the problem of the code that I show in the very first slides. So we will ask you how to avoid cold start issue, how to avoid the clock granularity problem, how to avoid and check that the compiler is not smart enough to eliminate some code, and how to avoid the problem of interference and in general of the performance variability. Right? So one suggestion I give you is also to look at how the stream benchmark fix all these problems. So the stream benchmark is taking care of all these problems. So you can go back to stream.c that we can provide in Canvas and see how the stream benchmark fix all these problems. So this is the last lecture. It is the last slide I have for this lecture. In the next lecture, we're going to look at performance modeling of a very important operation in HPC, that is the transpose of a matrix. Talk to you soon.